it claims that it will have intense colors. But is black a color? All right, so the harmonic oscillator. With our harmonic oscillator, the only thing that's going to be different from what we did before is we had potential energy was equal to 0 when we're in the well. We now have an actual potential energy value other than 0. So I have negative h bar squared over 2m times the second derivative of psi with respect to x. Plus the harmonic oscillator potential energy formula, which you do know. If we're dealing with subharmonic motion, what is the potential energy?
Like 1/2 kx squared.
Yes. This is a different K. This is a spring constant, or in this case, it's the oscillator constant. It is not the wave number. It is not kinetic energy. It is yet a different K. X squared times psi is equal to E times psi. So we need to figure out what are the energy levels and what is psi itself. All right, so what we need to do here is try to figure out some generic function for psi that would satisfy this equation. So that and again, this has been done for us. We're going to let psi equal some number e to the negative ax squared. If that's the case,
And why are we assuming that instead of the other sign?
because this works. You'll find that there are occasions where you have one that works and somebody else will publish a paper saying, oh, well, this also works. See, I wish I could remember the quote, or if I brought the book with me, but there was an author, I think it was in the Physics for Poets, who said that, in essence, quantum physics is filled with guesses based upon completely absurd logic, but just happen to come out to work. So, there are probably other functions that work. This one does work. We're going to go with this one. If you wish to pursue another avenue, you will feel free to. But sorry, not trying to dismiss it. It's a completely legitimate question. It really does come down to we've tried to find something generic that will work. Now, in essence, we are actually dealing with sines and cosines here. Euler's formula, e to the I theta, what is that equal to? See an incredible impact upon that. I'm sure you've seen it in math. Cosine of theta plus I sine of theta. So whenever I have an exponential, I can work sine and cosine into it. All right, so what's the derivative with respect to x?
Negative A, big A, little a, x. I guess there should be 2x. And then e to the negative ax squared.
Okay. We need the second derivative. So d squared psi over dx
x squared.
We got the product rule now. Rewriting it slightly differently. How do you do the derivative when you have two functions of x?
Negative 2 big A little a e to the negative ax squared plus big A little a squared times 4x squared, and then times e to the negative ax squared.
That was right.
Oh, I think I forgot the 2x. So it'd be,
You said 4x squared. That, I assume that you have that 2x times an additional 2x. Or did I mishear you?
oh, I would also have to add another 2x, right?
Then where'd that 4 come from?
Because when we have to bring another,
So when we did this the first time, that got popped out front. When we do it a second time, we're bringing another one out. So it should be a squared 4x squared. It sounds like you're trying to do the same, you're trying to do it again.
I think I blanked, yeah.
Okay.
Yeah, I think that's right.
You're in a warrior haze there. You're just speaking the truth without knowing it. So if I take this and I plug it into my Schrodinger equation, I have negative h bar squared over 2m times, oh, there was one thing you did miss though. Negative. Wait a second.
Didn't it cancel?
It does. Never mind. I was just joking about that. Times negative 2a, big A, little a, e to the negative 8x squared plus big A, little a squared, 4x squared, e to the negative ax squared plus 1/2 kx squared psi, oh, there should be a psi there, psi equals e psi. Oh, wait, nope, that psi does not belong there. Well, I know that psi though is big A e to the negative ax squared, so I can rewrite this as distributing h bar squared over 2m times 2 little a actually I want to factor out big A e, so big A e to the negative ax squared. So I'm left with negative 2 little a plus 4 little a squared x squared plus 1/2 kx psi, kx squared psi equals e psi. That is psi right there. So at this point, I'm not operating on psi anymore. I can cancel psi out. And so I'm left with h bar squared over 2m times negative 2a plus h bar squared over 2m 4a squared x squared plus 1/2 kx squared is equal to e. Double check that I didn't make a careless error in there somewhere. And I feel like I've got, oh, there's a negative there, so that's gonna cancel out, that becomes negative. Okay, I did make a careless error there. So we end up with h bar squared a over m minus h bar squared over m times 2a squared x squared plus 1/2 k x squared is equal to e. Again, double check, make sure there's not a careless error in there. I got a plus, got a minus, that's h bar squared a 2 x squared over m. Yeah, I think I'm good. All right, now this might not seem like much, but it does get us really close to it. These are dependent upon x squared. This is not. I'm going to write it slightly differently here. So I have h bar squared a over m plus 1/2 k minus h bar squared over m 2a squared x squared equals e plus 0x squared. If this is always true, then my coefficient of x squared, since energy is not, the total energy is not dependent upon where we are since it is conserved, this coefficient of x squared has to be equal to 0. And E is equal to h bar squared a over m, and 1/2 k equals h bar squared over m to a squared. Using that second piece over there, we can now solve for little a. So little a equals the square root of, so mk over 2 over 4 h bar squared. And if inspired, which equals the square root of mk on top and on the bottom to h bar. So we're one step closer. We started with a general equation of big A e to the negative ax squared. If this is going to work, then we have a value of little a, so we now have psi is equal to big A e to the negative square root of mk over 2h bar times x squared. And so then we have to figure out what psi is. I know that psi squared is equal to integral from 0, well, actually, from negative infinity to infinity. It's got to be equal to 1. And I did not actually solve for big A, so apparently I didn't need to do it. But we can find big A doing this. However, what I'm more concerned with here is the energy levels. H bar squared A over m. I know what little a is now. H bar squared is square root of mk over 2h bar m. That cancels out with one of those. I'm left with 1/2. I got an m and square root of m, so it'll end up being square root of k over m, h bar. And what's the square root of k over m? Think back to simple harmonic motion. What is the square root of k over m?
Is that period or frequency?
You're on the right track. It's neither of those, but it is related to those. Not frequency, but
Wavelength?
no.
Angular velocity, or angular.
Angular frequency.
Yep, there we go. So h bar over 2 times the angular frequency. It was omega naught. So if I actually plotted, and here's the big impact of it. So I have a plot here of energy versus position. It is, sorry, not energy, wave function. We've established, even though we haven't found big A yet, but we've established that we have, this will work. And that's a quadratic there, or e to the x squared. It's gonna look something like this, sort of bowl-shaped. But nowhere is the potential there. I guess it is energy. Nowhere is the energy infinitely large, which means that if I plotted my wave function into that, yeah, that would be V. If I plotted my energy into that, that it exists into the barrier. And that becomes a critical piece. We are not stuck with, oh, there's a wall there. It's, oh, the potential's not infinite. So there is a certain probability that this particle would exist inside the barrier. Keeping that in mind, we can then jump to, if I have a finite barrier, and I wanted to look at the wave function here, that the wave function, if v is equal to 0, I have some sort of wave hitting here, but when I get to a finite barrier, it's going to start to dissipate. So the farther I go into the barrier, the less and less of a wave function it is. But if my barrier has a finite disk thickness here, I have this wave sort of existing in free space, it hits the barrier, and so it starts to dissipate's the word I used before, that's not really the word I want, it starts to shrink. Not really the word I want either. But basically it's not 0 when it gets to here, and so there's a certain probability that the particle trapped inside here is going to exist out here.
Is it diminishing?
Diminishing is probably a better word. So let's go to the computer. Because in classical physics, if I don't have enough energy to get over the barrier, it's not going to exist outside the barrier. But in quantum physics, it might not have enough energy to get over the barrier, but there is a certain probability that it will tunnel through it. This is known as quantum tunneling. And there's this nice little video that I think sums it up, assuming that I can figure out how to get it to show up there. That one. Something happened. Oh. The best part about this is I'm recording all of this, and so there's some really nice video here of this thing video. And then it's gonna come in with the annoying Teams. That's probably why I didn't do it. Alright, so I want YouTube. Then quantum tunneling effect. Or quantum tunneling.
Some migraine attacks catch you off guard, but for me, a stressful day can trigger migraine attacks.
Quantum tunneling is responsible for many important phenomena such as the alpha decay of atomic nuclei and the